a real pleasure to welcome Frans Pretorius to give today's colloquium. Frans was scheduled to give an in-person colloquium in March, but at the time I remember he had a cough. So he canceled with our well-being in mind. But it's really nice to have him here via Zoom for today's colloquium. So Frans is a world-renowned expert numerical solution of the Einstein field equations, which describe the dynamics of space-time. And he focuses on the nature of binary black hole mergers. And he was the first to compute the in-spiral merger and ring down of the binary black hole system in 2005, which resulted in a prediction of gravitational waves that was rather spectacularly confirmed 10 years later by LIGO in 2015 with GW 150914, which matched his calculations amazingly well. So he's also interested in critical phenomena at threshold of gravitational collapse and the nature of singularities in black hole and cosmological spacetimes. And he also has investigated the signatures of small black holes which could be formed in particle colliders like the LHC. So Frans received his PhD in 2002 from the University of British Columbia with Matt Chaptwick, for which he received the 2003 Nicholas Metropolis Award for Outstanding Doctoral Thesis in Computational Physics from the APS. He was then a postdoctoral fellow at Caltech, then an assistant professor at the University of Alberta, and now he's a professor of physics at Princeton, and recently, or fairly recently, the director of the Princeton Gravity Initiative, which started a couple of years ago. Frans has won a bunch of awards, including a Sloan Fellowship in 2010, an APS Fellow in 2011, and a New Horizons Prize in 2017. So it's a real pleasure to have you here, Frans. And today, he's going to tell us about testing general relativity with black hole mergers.
Great, thank you very much, Andrew. Thanks for that generous introduction. And yeah, it's a pity that I can't be there in person. But yeah, these are trying times for all of us. So at least we have Zoom. You know, I think if this happened 10, 15 years ago, we wouldn't be able to do this. So at least we have that. You know, let me share my screen. That's working. Sorry, just give me a second. Can people see my screen share?
Yep.
And actually, what are people seeing? Because I don't get any feedback here.
We're seeing your Zoom window from the NYU Zoom.
Okay, do you now see the PowerPoint?
Yes.
Okay.
Oh, it was Frans, do you want to go into display mode? We're just seeing your PowerPoint.
Yeah. Okay, so sorry, I have not done a presentation like this again before. Let me just do this.
Yeah, perfect.
Oh, sorry.
Oops.
That worked. Okay.
Yeah, good.
Okay. Yeah, I had a second monitor connected. So actually, at this moment, I can't see anyone. So if there are questions, just interrupt verbally, and I'll try to answer any questions. Okay, yeah, so I'm going to talk about testing general relativity with gravitational wave observations of black hole mergers. Here's an outline of my talk. So I'm mostly interested in the dynamical strong field regime of general relativity. So I'll start and just give a brief description of what I mean by this dynamical strong field regime. And then I will describe some of the tests that have been done of GR with gravitational wave mergers so far. And the tests that have been the most stringent so far, or the most perhaps useful, that I'll describe a little bit, are essentially what I'm calling self-consistency tests. So in a sense, they're theory agnostic. They don't propose any particular alternative to general relativity. It's more consistency within the framework of general relativity. And the reason why they work and why they're actually pretty decent tests, despite having no alternative theory, is because of the uniqueness properties of black holes and general relativity. I'll explain a little bit about that. So if you want to sort of go a little bit deeper than these sort of agnostic tests, go beyond self-consistency tests, it would be ideal to have candidate alternative or modified theories of gravity to compare to. I should emphasize here, I'm completely classical in all of my descriptions. I'm not thinking about quantum gravity or things, things that might show up at Planck scales. These are sort of putative modifications to classical Einstein relativity that might show up at the scales of black holes in the universe. So for LIGO, it's going to be tens to hundreds of kilometers. So to go beyond these self-consistency tests, we need particular alternatives to relativity that we can actually contrast with. One reason would be that if we have particular predictions from alternative theories, we can actually dig deeper into the data than we can with self-consistency tests. So we can actually come up with more stringent constraints. On the other hand, perhaps one day we discover some anomaly. And then if we don't have particular models for what might be causing that anomaly, it will be difficult to say anything other than, well, something is wrong. So there are various reasons for wanting to consider these modified alternative theories. But then what I'll sort of argue is, at least in my opinion, in particular looking at black hole mergers, sort of the coalescence phase of mergers, at present there are, in my opinion, no interesting viable theories beyond relativity that we know of. And I'm not, that there are many, many viable and interesting alternative theories for other purposes. So I'll clarify what I mean by that. I'm not trying to upset anyone about their favorite theories. And then also describe sort of a case in point study of a candidate modified gravity theory, Einstein-dilaton-Gauss-Bonnet gravity, and sort of describe what some of these problems are. And again, thinking of it as a classical theory, trying to apply it to kilometer scale stellar mass black hole mergers. Okay, so to get us also on the same sort of page, this is all talking about Einstein's theory of relativity and possible classical modifications to it. So what I mean sort of by modifications to gravity is really modifications to geometric description of the nature of space and time. So Einstein's theory is a theory about space and time, and claiming that it can be described by a dynamical four-dimensional geometry. And so curvature in this, or how we experience curvature, is via, the Newtonian description is that is the force of gravity. And in Einstein's theory as well, the geometry is in a fixed background, but it's dynamical, it reacts to matter energy, and matter energy is responsible for producing the curvature that then we react to and experience as gravity. So of course, it's interesting just from perhaps a philosophical perspective that the same physical phenomena, that the force of gravity, can have two such incredibly different mathematical descriptions. One as a force, a Newtonian force, the other one as a curved space and time. And of course, if that's all that Einstein's gravity were, it would be curious, but it wouldn't necessarily be that profound. But of course, general relativity predicts more than just an alternative description for Newton's law of gravity. In particular, there are many sort of corrections to Newtonian gravity that have been verified in the solar system and various other places. But it makes, in my opinion, sort of three profound new predictions. One is the existence of gravitational waves, the small changes in the geometry of space and time that propagate at the speed of light. And then also it's got a qualitatively different regime of solutions, the strong field regime, which isn't present in Newtonian gravity. Of course, Newtonian gravity is linear, so there is no sort of strong versus weak. But in general relativity, there is a new regime of solutions, and that's where black holes lie. And also, incidentally, the large-scale structure of the cosmos, or the Friedmann-Robertson-Walker type equations, are also in the strong field, sort of offer, in a sense, qualitatively different behavior than what you might expect from Newtonian gravity. Now, general relativity doesn't have any intrinsic length scale, so there's no sort of dimensionful constant that says when things become strong fields. So it's a different theory from other theories that we might be used to, and it also makes it kind of difficult to exactly define what the strong field regime is. But so from my perspective, it's the regime where this new kind of nonlinear dynamic shows up that isn't present in Newtonian gravity. So for isolated star-like objects or compact objects, this happens when the compaction, or the so-called compaction, the ratio of the mass to the radius, and here with the g and the c squared, there are Newton's constant in the speed of light. So when g over r c squared roughly approaches order unity. So that some fraction smaller than that, that's where neutron stars lie. And when you get to that value around there, that's where black holes form. Of course, black holes, the nature of space-time changes profoundly when a black hole starts to form or when it forms. The interior undergoes gravitational collapse to a singularity, an event horizon forms that then screens us from the interior. It separates us causally, the interior from the exterior. So very different structure to space and time when this scale is reached. Now to get an idea of the dynamical strong field regime, now where we can have dynamics and in particular gravitational waves, it's kind of useful just to look at this sort of this dimensional analysis argument. So in general relativity, the leading order description of gravitational wave emission comes from the so-called quadrupole formula. So here I've got this with the power that's emitted by a time-varying source is given by essentially the square of the third time derivative of the quadrupole moment of the source. Again, g and c are Newton's constant in the speed of light. So the quadrupole moment is essentially the second moment of mass. So if we're just some dimensional analysis, if we take an object of mass m that's got a characteristic size of radius r, this is and it varies on a time scale of t. This is essentially the characteristic scale for the variation of the quadrupole moment. And if we say, well, how do we get to very strong emission? Well, the fastest that sources can vary in relativity is at the speed of light, essentially. So if we say that the time scale at which this source is changing is given by the light crossing time, then you actually find that the third time derivative goes like 1 over the radius. And so to get the most power, you want the most compact object. And so if we put in this, the criteria for the strong field regime together with maximum speed, we get that the power approaches the Planck luminosity. But that's curious. On one hand, you say, okay, this is just dimensional analysis, but remember again, I'm not talking about quantum gravity at all. So I haven't set h bar equals to 1. It's just that in Planck units, the Planck luminosity does not have h bar. So it's quite interesting that in a strange sense of the word, even without quantum gravity, general relativity knows that something interesting goes on when you approach the Planck scale. So this in sort of in a dimensional analysis, kind of a back of the envelope type of ways, what I mean by the dynamical strong field regime. Of course, in terms of solutions to the field equations, things do change drastically. Okay, so are there places in the universe where that's relevant? And of course, now we know the answer is most certainly yes. In particular for the strong field regime, there's been growing evidence, since the 70s, perhaps even the 60s, you can look back, that there's sort of essentially incontrovertible evidence now that there are places in the universe which have a lot of mass and are so compact that if general relativity is correct, they must be black holes. And I'm sure as everyone knows, this year's Nobel Prize in Physics was awarded for black holes, and half of the prize went to one of these observational pieces of evidence. So this rightmost panel here about the orbits of stars around the center of our galaxy, where now after the very sophisticated data observations that Gez and Genzel and their teams have made over a few decades now, they've essentially confirmed that there's definitely a supermassive compact object which is consistent with being a black hole. I guess another part of the prize went to Roger Penrose on some of the theory behind black holes. And also, as everyone knows, in the last few years now, LIGO has started to detect signals from mostly black hole mergers, but also one binary neutron star, possibly a few other neutron star or neutron star black hole candidates. And so, in the last few years, we've actually been able to start probing or observing this dynamical strong field regime via gravitational waves. These are just a sort of a smattering of a few of the events that have been observed. And incidentally, I'll sort of be focusing on this 150914. That's the first event that LIGO observed, this merger of two roughly 30 solar mass black holes. And actually still today, it's in terms of signal to noise, and perhaps in terms of how visible the signal is in the waves in this plot, it's still one of the best candidates, and also one of the best candidates for testing relativity. Okay, so we're now starting to get data about the strong field regime, and of course, one whole aspect of this whole endeavor of gravitational wave astrophysics is to learn about the universe, learn about populations, etc. So I'm not going to talk about any of that, which is very interesting. But what I want to talk about today is, well, how can we actually confirm that what we're seeing here is coming through dynamics, which is governed by Einstein equations, the Einstein equations, and that the black holes, the disputed black holes that are involved are actually essentially Kerr black holes. Sorry, wrong direction. So we want to use these gravitational wave observations to test general relativity. And so our observable is this essentially one-dimensional slice of the gravitational wave emission. So it's just this. So here, what I'm plotting here is the LIGO, Hanford and Livingston filtered strain data from the 150917 event, together with, in this black curve, is the sort of a best fit numerical relativity waveform that matches the data. And so you can see it's a decent match. Sort of the early part of the signals, the in spiral, then they coalesce, and then it rapidly rings down to a quiescent black hole. But if you look at it, well, this is the data. There's, to some extent, it doesn't seem like there's that much information. How do we even conclude that these are two black holes that have merged, let alone try to get some more information and say that this is actually constraining the theory of gravity. So perhaps before I say that, let me just also show one of the movies of this event, simulation. So this is by the Caltech-Cornell-CEDA collaboration. Presumably people have seen many of these kinds of events, but I think it's just useful just to look at this again. So this is a simulation of the 150914 event. So those two black circles there are the black holes, a 36 and 29 solar mass black hole. But one thing to sort of appreciate about this is when I play the animation, it's going to be about slowed down by about a factor of 100. And notice the scale here. So this is about 1,000 kilometers. So this image spans a few thousand kilometers. So this really tells you that these black holes are moving very rapidly, 20, 30, 40% the speed of light. So it's a very dynamical system. There's a lot of energy. And so it's pretty cataclysmic collision. So what you see here with this green sort of mist, and this is the gravitational wave emission that's being produced by the binary motion. So you can see the two black holes are in orbit. They're producing these gravitational waves. The gravitational waves carry energy from the system. And here you can use your Newtonian intuition that if the system is losing energy, it's got to become more tightly bound. So they spiral in. But that increases the rate of emission because they're now closer together. They're moving faster. So it's a runaway process. And eventually they collide and they merge and they form a single black hole. And there's this burst of radiation from the collision, but then very rapidly it rings down to a quiescent Kerr black hole. And so what LIGO has measured is, so this radiation is streaming out in a pretty complicated pattern through 3 dimensions in space. But we're at some point along the line of sight of this event, and we're getting this one-dimensional slice of that data. And so here, again, the early in spiral, the merger, and the ring down. Okay, so how can we justify having with seemingly such a sparse amount of data from this full 4-dimensional space-time? Can we say that we can test general relativity? I mean, how do we go about doing that? And essentially, these self-consistency tests, pretty much all of them work because of the so-called final state conjecture. And there were many people back in the 60s and 70s that sort of came to this same idea, but this is kind of the way in which Penrose phrased it. And this final state conjecture says that begin with generic initial data in an asymptotically flat space-time, satisfying the vacuum Einstein equations. The conjecture was if there are no naked singularities in that initial data, the final state will be a set of unbound black holes moving apart from one another with gravitational radiation streaming away to no infinity. And moreover, if you zoom in on any one of these black holes that are now sort of becoming increasingly isolated, you will find that the local geometry around one of these black holes asymptotes to a unique member of the Kerr family of solutions. So the Kerr family of black hole solutions, it's the rotating black holes. The two parameters are the spin and the mass. So if you take this conjecture and you restrict it to a single black hole spacetime, this is sometimes referred to as the conjectured nonlinear stability of Kerr. And I think mathematicians have been working on this particularly, I think, intensely over the last couple of decades, and I think they're getting quite close to proving it. If you restrict to a situation where there's no radiation, you just have a single isolated black hole, and this is the celebrated no-hair theorem, which is, again, almost a theorem at this stage. It's pretty much been proved. And essentially what it says is that if you look at stationary spacetimes, the only spacetimes in an asymptotically flat four-dimensional spacetime that has a non-singular horizon are the Kerr family of solutions. Okay, so now you may immediately object and say, well, how is this going to allow us to test relativity? We don't live in a vacuum universe. We don't live in an asymptotically flat spacetime. And yes, you're correct. And so applying this idea to testing relativity, we have to assume, and I think it's a reasonable assumption, but that's something that could be questioned. So that's why I put the question mark, whether this is a reasonable assumption, that the kinds of black hole mergers that we expect in our universe, for instance, those two the 30 solar mass black holes, that in their circumvariant environment, the mass is so small compared to the mass of the black holes that it's essentially a negligible perturbation on the dynamics of the black holes, and therefore the structure of the gravitational waves that are emitted by the merger. And then moreover, okay, we're not in an asymptotically flat space-time, but once these waves are generated, they're going to propagate through the universe. And essentially the only effect of being in an expanding universe as opposed to a flat universe is there will be a redshift. And then also there might be occasionally lensed events. So there could be lensing and there could be redshifting. But essentially the structure of the waves emitted by the source is unaffected by the surrounding matter. And so it's really, it's all of this that sort of underlines all of these self-consistency tests within relativity. And I'll just mention a couple of them. So the one test is a so-called residuals test. And still, the best single black hole example is 150914. So I'm showing it here. And the idea is, so LIGO's got this measure data. So you take the best fit general relativity template of this event, you subtract it from the signal, and you look at here what's left over, what's the residual. And if it's consistent with noise, you conclude that, yes, that was what LIGO saw. It saw that particular event that you've got in your template bank. But then again, you might ask, okay, so how do we say that why is it a test of general relativity and not just a statement about consistency about the event that we have observed? And for example, you might turn it around and say, like, what if eventually LIGO does measure a residual? What if they do this subtraction and they find a residual? Why would we say that this is strong evidence for modified gravity, as opposed to, for example, a novel kind of black hole merger that hasn't yet been modeled? And the reason is this final state conjecture. In general relativity, if we mapped out this 9-dimensional parameter space of Kerr black hole mergers, so the two masses, 3 parameters each for the spin vectors and their centricity, we're done. That's it. There are no other black hole mergers possible in general relativity. And then the caveat is, of course, modulo a circumbinary environment. So if there's a residual, okay, there must be some anomalous environmental effect that's causing it, which would be pretty remarkable if it can affect black holes to a point of the gravitational waves, or there's got to be something that we're missing with general relativity.
Frans, could I ask a question there?
Yes.
Couldn't it also be a neutron star black hole merger, or some other compact object like that, as opposed to a modification of gravity?
Yeah, good question. And so in that case, it sort of depends on what part of the signal you're getting and if you're getting a large enough signal to noise. Because what will differentiate black holes from near black holes like neutron stars is tidal deformability. So the neutron stars, they will, in the early stages of the in spiral, it will look pretty much the same. But at the late stages, you will start to see the deviation based on tidal effects. And actually, if the merger of the two neutron stars is in band, which for LIGO, unfortunately, they're not, that's a too high frequency. But if you can imagine a detector that would go to 2-3 kilohertz, you'll actually see the merger part in band, and that will occur at a different time. It will occur earlier in the signal than two black holes of the same mass would have. So if you can see the merger, it would be very different from GR. And in LIGO, at least, you'll start to see signs of it being a little bit different. But you're right, for any of but the brightest neutron star merger events with current LIGO, it would be difficult to tell them apart.
Yeah, I guess my point is just that if you're going to say that any residual is evidence for a modification of GR, you probably need to qualify.
Yeah, right. So
it's not a compact object. It's not a neutron star, but it's it's due to some modification of particle physics or something, but not GR. We don't know.
Right. So for example, if LIGO saw, say, what they identified as two 1.4 solar mass objects with a signal to noise of 10, something pretty low, and they said, oh yeah, there's a hint of a residual, no one's going to take that seriously. And I think they'll know the difference. If it was something, a binary neutron star, something that could be consistent with a neutron star, and there was a significant residual, I guess so if there was a residual that was analyzed with vacuum templates, then you'd want to ask, well, could the residual be a consequence of things about neutron stars that we could model, such as, did we not include tidal effects? And actually, LIGO does include tidal effects. So if you want to include neutron stars in this thing, you'd have to expand the parameter space for those tidal parameters. And I think with something, if they were neutron stars, then now there's also matter involved. So, and then the matter is significant in neutron star, right? So that's not just an insignificant circumbinary environment. The bulk dynamics of the matter is important. And we definitely don't understand matter at those nuclear densities to be able to conclusively say that if there wasn't something strange that was associated with something like a neutron star, that it might not be associated with things that are not general relativity. Yeah, so that's correct.
Frans, this is Kyle Kramer. Could I ask a question here as well?
Yeah, sure.
So I'm curious if that I know this is a colloquium, so the way that you're trying to describe things in a very intuitive way, and that's great. And but in terms of the actual residual test, is it literally done in the way that you described, where you sort of just take the best fit value and subtract it off, and then somehow ask if it's consistent with noise? I'm just thinking that, so I do a fair amount of like statistics things in more of a particle physics context, and there, if you really just have, in some sense, like a null hypothesis and you're trying to test it, and it's like a goodness of fit test, it's sort of an underspecified problem. And maybe that's kind of where you're going from the introduction about sort of introducing, other kinds of deviations around GR or something. But, if you really wanted to do that carefully in some statistical way, you certainly wouldn't want to just like subtract off the best fit and do some.
Yeah, so I'm you're right. So I'm oversimplifying it, but I'm also actually I haven't done these residuals tests. So this is what LIGO has been doing, and they've been much more careful about it. And I actually don't know the exact details about what they're doing, but yes, they are definitely more careful about the statistics in ways that I don't know. So I can't exactly answer your question. But I think you are correct in the sense that how sensitive is something like this? I think ultimately it's less sensitive to, say, a hypothesis test where you have, say, a template bank from some alternative theory versus a template bank from general relativity. You do the same kind of analysis and you say, does the data favor one versus the other? And so I think if you had particular concrete models of effects that were in general relativity, you could say stronger statements than you can with these residuals.
Okay, and so I don't know if that's where if you're going in that direction at all later on in the talk, or or not really in terms of
Yeah,
sort
well,
of thinking about.
that will, first
in
of all,
your-
really
in
what
your
I want to say,
introduction,
that
it
will
sounded
be,
like.
sorry, that'll be an argument for, it's one argument for exploring particular alternative theories. But I won't be going into the details of that anymore. So I don't know if you have another question about that.
No, that's fine. I appreciate it.
Okay. So another class of this consistency test is, again, so that if this final state conjecture is correct, and we see what we would think is near a vacuum, a binary black hole merger, there are not very many sort of numbers that fundamentally control as much information as we in principle can get out of a template. So if it's a signal. So if it's a high SNR signal, in principle, there are many numbers that you need to describe it to that level of accuracy. But the final state conjecture says underneath that, there really a small number of parameters. So another way to sort of try to get a hold of this sort of self-consistency in a way that's perhaps a bit more intuitive than just this residual test is to look at parts of the signal independently. And here's sort of a common one that's been done. And this is looking at measurements of the final mass and spin of the remnant. In the first instance, only using the in-spiral data. In the second case, only using the ring down data. So if you just look at the in-spiral part of the waveform, if there's enough signal there, you can infer the parameters of the binary from the in-spiral alone. And then general relativity uniquely tells you what the final mass and spin of the remnant has to be. And so that's one estimate of the mass and the spin. On the other hand, if you have some ring down data present, you can ignore the in-spiral. And again, because of the uniqueness properties of black holes, the way that a black hole rings down is very particular to its mass and spin. So if you can measure the frequency and the decay of the ring down, that essentially tells you what the mass and the spin of the remnant are. So those are in some sense taking two independent pieces of the data, at least from in time, two independent in time pieces of the data, and extracting essentially what's the same numbers, and they have to be consistent. And here's an example using several black hole events from a LIGO paper. And if you sort of want to kind of quantify the level of consistency with general relativity, perhaps general relativity, roughly the entire range of possibilities is in this diagram here. So the fraction of the area of what is some combined 95% or 90% confidence interval relative to this diagram. So this is perhaps a 10, 20, 30% accurate test with this measure. Okay, there's another, again, you can do this, you can further pick apart the in-spiral piece, but let me just skip over that because it's the same kind of idea. Okay, so what if you want to go beyond consistency? So there are a couple of things that are, at least that I find a little bit unsatisfying about that. Okay, on one perspective, we can say, well, let's wait until there's a residual or a problem and then worry about it. On the other hand, if we say that that LIGO is confirming relativity, it's confirming the Kerr hypothesis, this final state conjecture to some level. Well, if we don't know what the options are, it's a little bit unsatisfactory. Like, what are we ruling out? Like, what could it have been that we're now saying with the data that it's not? Another sort of a reason to try to go beyond consistency and actually compare it to particular alternative theories is, as I mentioned before, is there are various subtle effects, things like parameter biases that you might miss with something like a residual. So you can dig deeper into the data. And then another point is, well, what if a residual, some inconsistencies eventually discovered? If we don't have particular ideas or models about what that might represent, how can we interpret it? How could we be sure that it isn't some environmental effect or some kind of compact object within relativity, like neutron stars that we haven't understand? At least with neutron stars, we can to some extent model them. To really go beyond these self-consistency tests, we need to understand how gravity can be different from relativity, and then construct models for those kinds of modifications. Now, there are numerous modified gravity theories, and I admit that in this case, applied to stellar mass black hole mergers, there isn't yet a good motivation for modifying gravity. There's definitely, of course, at the quantum gravity, at the Planck scale, we need, relativity doesn't work there. And if you want to address dark energy, dark matter, perhaps the early universe, inflation, alternatives to inflation, there are very good reasons why it's sensible to consider modified gravity. So part of the motivation is admittedly a bit weak here, applying it to black holes. But in any case, there are numerous modified gravity theories, and many of them have been solved in the perturbative regime. So by perturbative regime, I mean either perturbations to the in-spiral, so taking these post-Newtonian expansions of in-spiral and seeing where new effects come in. Essentially, almost like if you consider a neutron star a perturbation to a black hole, there'd be tidal effects coming in. So you can also at the perturbative level look at how modified gravity theories come in. And then also some of these modified theories have novel black hole-like solutions, and people have looked at perturbations of those. And so you can see how they modify the ring down structure. So in those two senses, quite a bit is known. On the other hand, so I'll say there's essentially nothing known about modified gravities theories that is relevant to the actual coalescence phase. And if we're interested in the sort of dynamical strong field gravity, that is the most dynamical strong field part of the solution. So if there's anything interesting going on in this regime of relativity, that's where we have to look. And so the question is, well, perhaps there will be hints of that in either the ring down or the in spiral, and that's certainly possible. But how much of the signal are we missing if we don't include that part of it? So I like to as just a visual of that, to just go back to this signal. So here again, I mentioned these are the two LIGO observations. And then the numerical relativity waveform there in black has been whitened, if you will, with the noise curve of LIGO. So LIGO in this regime is less sensitive to low frequencies than it is to the frequencies around the merger. And so just to illustrate, if we had an equal sensitivity detector, equal sensitivities to all frequencies, this is what the signal would look like. So unfortunately, with these heavier black holes, these 30-40 solar mass black holes, LIGO doesn't really see much of the in-spiral. So most of the signal is coming from this merger regime. And so if we can't access that with our tests of relativity, or comparing it to modified theories, we're really losing a lot of the signal. So where are we in terms of understanding modifications to relativity in that regime? And I would argue that at present, there are no interesting viable modified gravity theories applicable to this merger phase. And yeah, I just like putting up this picture. This is an illustration by Kip Thorne that was more than 20 years ago, and he used this to motivate us to understand the problem in general relativity before we could solve it in relativity. So in relativity, the question mark has been removed, but in modified gravity theories, we don't understand the merger phase in any interesting viable theory. So let me explain what I mean by interesting and viable. And so what I'm calling here an interesting theory, and it's again just for the purposes of testing relativity in the strong field with binary black hole mergers, is a theory that is consistent with existing tests or experiments in the weak field, but can potentially offer a significant observable difference in the strong field. So there are definitely sort of modified gravity theories where we know what goes on, say scalar tensor theories, but for binary black holes, the majority of them, nothing happens. It's the same expectation as relativity. So I would call that a non-interesting theory for this respect. Then I will call a modified gravity theory viable is if we can solve it and make predictions of what's going on in this regime. So again, I'm thinking about classical gravity here. So solving the classical equations of motion of this putative modified gravity theory, if it possesses a well-posed initial value problem, so we can actually make computations and come up with concrete predictions. So for example, again, scalar tensor theories, they're definitely viable. A large class of them have well-posed initial value problems. But as I'll get to, like things like EdGB and some of the other ones that perhaps are both potentially viable and interesting, the viability is something that is at least, I don't think there's really any theory that really satisfies both these criteria in the dynamical strong field. But it's also just getting back to just another theoretical, just sort of curiosity-driven motivation for understanding modified gravity It's just, even if at the end of the day, Einstein gravity is perfectly accurate for astrophysical black holes, we don't have any modification. It's still an interesting question. What is going on in the strong field regime that if it really is Einstein gravity, and if it happens to be unique, what could possible metric theories of gravity give for a strong field solution? And perhaps by analogy, I'd motivate this. If you wanted to ask the same question for the weak field regime, the propagating degrees of freedom, you can ask, well, if you have a metric theory of gravity that has gravitational waves, what are the possible structures of the waves in the weak field? And there we know the answer, and that generically there are 6 polarizations that are possible. So in the weak field, general relativity is just one amongst many conceivable theories, and depending on the theory, you can have very, very different structure in the weak field compared to relativity. So the analogous question will be, for generic metric theories of gravity, what is a conceivable sort of strong field regime? What are the soliton-like solutions that those theories allow? And if somehow something miraculous happens and that they all have to be Kerr-like black holes, that would be kind of astonishing. We really just have no idea at the moment about what non-GR theories look like in this regime. Okay, so
Frans, can I ask you a question?
Yeah.
It seems a little bit artificial to me, or rather that question is not tied to a physical scale. Typically, when we talk about modified gravity, we refer to either very short distance scales at which we expect general relativity to break down because it does have in it dimensionful parameter, dimensionful coupling constant, and that would be a regime of quantum gravity, or maybe at ultra large scales where there is cosmic acceleration and we don't quite know, and try to explain that. Now, in this particular case, I do not know why general relativity should be modified one way or another. You can always argue, yeah, well, still, it's interesting. It's an interesting question. But then the question is about the scale. What is the scale at which you are expecting that gravity changes? Either in terms of dimensionful parameters or in terms of strengths of your fields. And so because you have diverse phenomena to describe, collisions of black holes, neutron stars, all sorts of other objects, is there more concrete formulation of the question that you are asking? At what scale do you expect that to happen?
Yeah, that's a good question. And I think in terms of the motivation, sort of as I mentioned before, I think sort of a physical motivation for studying differences that come in at the kilometer scale, or perhaps they're not at least there's no data that points to us having to look for such modifications. I mean, I think there are some interesting physical ideas like these ultralight axions or ultralight particles that could have Compton wavelengths of this scale. But this would sort of be null physics that changes black holes, not because of relativity, but because of other matter effects. Right, so I agree that generically, if we expect differences to come in, at least one very sort of sensible way of thinking about this is that there's going to be some kind of scale where new physics comes in. But what I'm talking about with this slide specifically is if we just think about sort of a metric theory of gravity. The thing that's interesting and unusual about relativity is that there is no length scale where things are strong versus weak. Right? So, for example, you can have a black hole that's a solar mass looks exactly the same from a relativistic perspective to one which is 1 billion solar masses, or one that's a Planck mass. If you ignore quantum gravity, just as a classical theory. So there's no scale. So, but there's definitely a very different regime of the theory where gravitational collapse to singularities happens, but that doesn't occur at any particular scale in the theory. So yeah, I'm sort of asking the question: are there, if you consider, let's say just for example, if we look at just higher dimensional Einstein gravity, we know that if we go beyond 4 dimensions, we can have black rings, we can have black brains, we can have black spheres. There are many more interesting, complicated horizon-like solutions. Why is that not possible in 4 dimensions? Can we have modified geometric theories that have more interesting horizon-like structures? Could there be theories that have horizonless sort of gravitational geons, for instance, sort of soliton-like solutions? So So with this slide, that's kind of what I was kind of addressing, those kinds of questions.
Yeah, but by now, we understand a lot more about general relativity, actually, because we can talk in terms of just pure degrees of freedom. So if we insist that there are only two helicity states of a graviton, then necessarily you will get general relativity. There is no other theory that you can get, any other consistent theory that you can get. So that's a theorem that you can prove. So if you want more degrees of freedom, sure, you can add axioms or make it massive or whatnot. But in every single case, you can classify the theory as to what do you get and classify the terms of interactions just by basic principles, the number of degrees of freedom, Lorentz invariance, and so on and so forth, and number of course space-time dimensions. So in that, and also in general relativity, there is a scale. That's a Planck scale. I mean, in the fundamental theory, of course, you introduce masses in it, and you can introduce different masses, and then you can compare your distances to the corresponding Schwarzschild radii. But those radii are defined by the masses that you introduced. But fundamentally, there is a scale that's Planck scale. That's where quantum gravity will kick in. So, and that's where the singularities are, actually. If we ever hope to resolve those singularities, the resolution should kick in at that scale.
Yes, I'm not disagreeing with you. I think like when I sort of explain the problems of these classified, modified gravity theories, it might also be another way of saying the same thing, that if we impose things like, in this case, the classical well-posedness of the equations of motion, you do sort of get, the answer might be that you do get a unique theory in its relativity. So that might be the problem. And you've said it in different ways in terms of degrees of freedom and things like that. So it might, at the end of the day, this mystery might really not be a mystery, and that it actually is unique in that sense.
Yeah, certainly those things are related, the degrees of freedom and the posedness of Cauchy problem, yeah.
Okay, actually, see, so yeah, I'm also going a little bit slowly. So let me I'll go through this last bit a little bit quickly. There's, at least just from the kinds of equations that we get for these modified EG things, there's a few interesting things we want to get to. So I'll go over this very, very briefly for the sake of time. So, okay, how do we modify general relativity? I've sort of got here three broad classes. You can modify the coupling between matter and geometry, try to modify the geometry, try to modify the matter, and perhaps exotic alternatives to black holes. In many cases, they're not distinct categories. You can sort of shift one into the other. But just in the sake of this classification, let me just sort of focus on modified geometry. And so one sort of usual approach where you can think about doing that is, well, it's a geometric theory. So let's start with the Lagrangian, the geometric Lagrangian, the Einstein Hilbert action. And so for Einstein gravity, that's given by the Ricci scalar. And so you can try to think of adding other curvature scalars that you can construct from the Riemann tensor to the action. The problem with doing that is that, except for one, other than the Ricci scalar, there's only one other special scalar, the Gauss-Bonnet scalar, that if you did add them to the action, you would get equations of motion that have more than second derivatives. And those are generically ill-posed. They don't possess any kind of well-posedness properties. Okay, so let's look at this Gauss-Bonnet scalar then. And so the one problem in 4 dimensions, and perhaps again, this points to why perhaps general relativity is the unique answer in 4 dimensions, is this Gauss-Bonnet scalar in 4 dimensions doesn't affect the equations of motion if you just add it with a constant coupling. So below here, I've sort of got the Lagrangian, the Einstein Hilbert piece, the dilaton with the kinetic term. And if you didn't have this phi coupling here or some coupling to the dilaton, this last piece would just be a total divergence in 4 dimensions, and it wouldn't affect the equations of motion. So to get Einstein-dilaton-Gauss-Bonnet gravity, you couple this Gauss-Bonnet scalar to the dilaton, and then you break this divergence property, and you get non-trivial modifications at 4D. And incidentally, you can also map this to sort of one of the Hondesky class of sort of scalar tensor theories. So you can shove all of this into the matter sector if you wanted. Okay, so why might this be possibly interesting in the way that I've defined it? And the one thing that's interesting about EdGB gravity, so now you've introduced an actual length scale, this parameter lambda. And in EdGB gravity, black holes only exist above that scale. And moreover, they acquire hair, if you will, they acquire scalar hair. And for black holes that are close to the scale, it can be as up to around 10% of the mass of the space-time can be in this hair of order of magnitude. So it can be quite significant. Incidentally, of course, there's actually an issue if this field were there, and if it were cosmologically significant, the binary neutrons, it would change the speed of propagation of light, and the binary neutron star merger would have essentially ruled out this version of it already. So here we have to assume that this kind of scalar is only sourced by strong curvature. It's not present in the cosmos, which might be, again, another artificial argument. So the question is, well, is this viable? Is this, okay, it's got second order equations of motion, but that's a very low bar to cross for well-posedness. There are many other, there are many examples of equations that are second order that are ill-posed. So is it well-posed? And so on the optimistic side, well, other than being second order, so Kovacs and Rial have proven that if you start with solutions to Einstein gravity, you get small coupling, so the lambda is small, and sort of linearized perturbations, then it is well-posed. On the other hand, if you look at the full equations, there's some very nasty nonlinear terms, and it's been suggested that rather generically, you would form things like shocks and singularities. So to start with getting a handle of this is work that I did with our former student, Justin Ripley. We want to look at the full EdGB equations, but in sort of the simplest scenario that we could sort of easily get a handle of, and that's spherically symmetric gravitational collapse. I should say recently, Will East and Justin Ripley have also extended this to situations without symmetry. And at least the conclusions that I'm going to give you about well-posedness are consistent with that. And so the optimistic side is actually we don't see any of those shocks and singularities suggested by some of the earlier work in spherical symmetry. We get, it seems at least as far as we can probe this numerically, these hairy black holes, when they exist, are stable, even with large perturbations. But the pessimistic side is that even when you're in the weak field, so space-time is almost Minkowski, if you make this coupling parameter strong, and I guess that's not surprising, especially from a field theoretic perspective, but if you make that parameter strong, the equations change character from hyperbolic, and they become essentially mixed type. So perhaps for the sake of time, let me show, I'll skip a lot of the stuff, but just in words describe what we did. So we took in spherical symmetry, a pulse of this dilaton field, varying the coupling, and just watched its dynamics. And in some cases, we could go to the strong field GR regime and form black holes, and they develop this hair. But the case that I want to focus is even the case where we were far from forming a black hole, we could tune up this parameter where the light cone structure, or sort of perhaps the sonic structure of this additional degree of freedom breaks down. And that's what I'm demonstrating here. So this is an example of a collapse of this spherically symmetric evolution. And this is in spherical polar coordinates. So this is just looking at a certain regime in R. So just an outer shell, and the vertical axis is time. In this bottom figure, I'm showing the space-time light cone. So this is, if you will, almost like a Penrose diagram. So those are the ingoing and outgoing characteristics in orange and blue. And you can see it's pretty much Minkowski space-time. But if you look at the characteristic structure of the dilaton field, you can see at some point they start to twist over. And here, when this black region is they actually become imaginary. So they start having characteristics. And so you characterize the equation as elliptic in that region. So in some sense, we start with valid initial data, and we evolve up to a point, and then it loses hyperbolicity. And interestingly, when it loses hyperbolicity, everything is still smooth. We don't see any singularities, anything unusual happening in the field. In fact, it looks very different to it's very similar to the GR simulation. And again, for the sake of time, I won't show these things. Because it takes a bit of time to explain. People that are interested in, I can show them those afterward. But so what is this implying about the viability of this theory when that happens? And interestingly, because there are no shocks, there are no pathologies, everything looks fine. It seems like perhaps some mathematical sense of these kinds of equations can be made. And actually the answer is yes, at least qualitatively. If we sort of think like what's happening with the characteristics here, you can see that they sort of approach what's called the sonic line in the literature of mixed type equations. They approach in a way which suggests that the EdGB equations are of so-called Trichomy type. And back in the 70s, Morawetz studied these equations, and she actually proved uniqueness and existence results for the Trichomy equation. And essentially, she was motivated by sort of transonic flows over airplane wings. So mixed type equations, they definitely appear, in various situations, and you can make sense of them. On the other hand, if we want to say, well, these are theories that we can use to predict what happens with black hole mergers, that means that we want to give some initial data. We want to view these equations as having a well-posed initial value problem. And looking at Morawetz's proof, I think that makes it essentially almost a no-go for these kinds of mixed type equations. And so let me just briefly explain that in the last couple of minutes. So the two canonical mixed type equations are the so-called Trichomy equation and Keldysh equation. So these are, if you will, the analogs of the prototypical hyperbolic wave equation, parabolic heat equation, and elliptic Poisson equation. And so you see it's like a wave-like operator, but here for the Trichomy equation, it's multiplied by y, and the Keldysh equation by 1 over y. And so it's elliptic in the positive y plane, hyperbolic in the negative y plane. The so-called sonic line is the point where it transitions from one to the other. With the Trichomy equation, the characteristics of the hyperbolic equations, sort of illustrated here with these white arrows, they run into the sonic line tangent, sort of orthogonally, and the speed goes to 0 at this point. Whereas in the Keldysh equation, it runs in tangentially and the speeds diverge. Actually, the Keldysh equation is much worse, as you can imagine. There's you get serious sort of shock-like problems at the sonic line. On the other hand, things are very well behaved with the Trichomy equation at the sonic line. And so what Morawetz was able to do to prove sort of uniqueness and existence is she looked at this equation, but she found that to be able to do that, she looked at this domain bounded by these segments A and B. So A and B are along characteristics in the hyperbolic part of the equation. C is just some smooth curve in the elliptic part. And she found that you can get a unique non-singular solution in the interior, but only if you specify data on one of the hyperbolic characteristic surfaces and on the elliptic surface. So you couldn't specify free data on both the branches of the hyperbolic surface. And so if you can imagine, in some sense, this equation, even if you start in the hyperbolic region where you think you can freely specify initial data on both characteristic surfaces, that's not possible with this kind of equation. Somehow it knows that at some point things are going to become elliptic. And okay, so even though this, you can make sense of this in a mathematical way, you can get sensible equations, I think it's essentially dead in the water for a predictive theory in the sense of being able to have a well-posed initial value problem. So just the last slide before my conclusions. So is EdGB gravity then not viable? And okay, you can wave, if you wave your hands enough, there's still a region of parameter space that you can argue it might still be sort of viable for the purpose of foil to test against general relativity for black hole mergers, and that is if you take the smallest black hole that's allowed in this theory, so given by that scale, and you say that there's no, if you then consider ordinary matter in the universe, if there's no matter in the universe that's more dense than the effective density of that small black hole. So for example, take a solar mass black hole. The effective density of that is several times nuclear density, so several times more dense than a neutron star. If you say there's no matter in the universe that's more dense than several times that of the nuclear density, you won't trigger this failure of hyperbolicity. And of course, you're going to say, well, okay, that might be fine today, but going backwards in time, early on in the universe, you're definitely going to violate this condition. So if you want to sort of treat this as a viable theory, you've got to somehow change things in the early universe. I think if I did sort of back of the envelope calculation, it's okay until Big Bang nuclear synthesis, but if you try to push it a bit further, you'll start violating that condition. So I'm sort of personally more on the pessimistic side for EdGB gravity as an interesting vehicle to test black hole mergers, but there still is a sliver of parameter space where it's interesting. Okay, so to conclude, I think that we're really in an exciting new era with gravitational wave observation of the universe. And despite what I've been focusing in this talk about some tests of gravity, arguably in the sensible modifications to gravity, a lot's going to be learned just about the astrophysics of compact objects. And so that's definitely going to happen. Whether we discover some novel physics in the strong field regime, that's less clear. But I think one thing, at least, that for what we have now, that we have data from the dynamical strong field regime, essentially the gauntlet's been thrown down for modified theories or theories that predict some exotic alternatives to black holes, because now they have to confront the theories with the data. And just again, from a theoretical perspective, I still think ignoring quantum arguments or the arguments from field theory, just thinking about classical theories of geometry, it's still a bit of a puzzle why the strong field regime in relativity is possibly unique in 4 dimensions. So thank you for your time.
Let's thank Frans. And you already had some questions, but if there's more questions, let me look at this list here. So David Greer.
Hi, I'm from a very different branch of physics, and so this may be an elementary question, it probably is. So I was wondering if the black holes are accelerating into the collapse, wouldn't that modify the Hawking radiation that they emit? And wouldn't that also carry away energy and information from the merger? And so wouldn't that modify the final state conjecture?
Yes, so I think with stellar mass black holes, the Hawking radiation is extremely insignificant dynamically. So it's the temperature of solar mass black holes, I think if I remember the number, it's on the order of nanokelvin. So the dynamics might change that, but it's not going to change it by orders of magnitude. So to make it relevant, it will have to change it by many, many dozens of orders of magnitude. I don't, at least my initial naive impression is that that's not possible. So yes, the Hawking radiation does change things, but at least for the very large black holes that we see in the universe, it's completely insignificant.
Okay, Massimo.
Yes, I have actually two questions. One, in this dilaton-Gauss-Bonnet gravity, you have what for a particle theorist is an operator of dimension 5 with a coupling constant that is that lambda. Lambda is of the order of 10 kilometers. So the mass scale, the energy scale is the inverse of that. Wouldn't that make it a very strongly coupled theory at very low energies? Because
yes, yeah, you're right. So I think like in some sense, like when I argue like this is a what would be the right word? Let's say it's an issue, I think, with applying these kinds of theories to modifying or to looking at scales of 10 kilometers, and that it's very artificial to take parameters that you might expect to be at sort of relevant to might show up at some small scale, whatever, string scale, Planck scale, etc., and then blow it up to on the order of kilometers. So it's, yeah, I don't think there's a good justification for doing it, other than in some cases, well, we can try, we can.
So the second question is a bit political in a sense. You showed Penrose. Penrose had singularity theorems. Singularity theorems say that you have a black hole if the cosmic censorship hypothesis works. And in Princeton, actually, there is a very good mathematician that studies these problems, is the Penrose. So I wonder if there is any collaboration between, say, you or the numerical people and the people who studied in GR, I mean, the mathematicians who studied GR and problems like cosmic censorship, etc.
Yeah, there's not much in the sense of like formal collaborations, but yes, we definitely discuss these issues a lot. And I think the one barrier that's a bit difficult to overcome is in some sense that the theorems that they're able to prove are often very general. And for example, like the kinds of numerics that we do, it's like specific instances. And sort of going from something that's sort of general conditions to specific instances takes a bit of an effort. But that's actually what Andrew mentioned in the introduction, this new gravity initiative at Princeton, that's partly been founded to try to overcome some of those barriers. So it's sort of a collaboration between mathematics, physics, and astrophysics to look at all things strong field. And actually, you know, with regards to sort of cosmic censorship and black hole interiors, we have, it's a very difficult problem numerically to sort of to look at these kinds of situations, because you have to be delicate about situations where singularities might form, but at least in 2+1 dimensions. So forming BTZ black holes and looking at those interiors, we've started being able to look at some of those issues, and we have been talking with De Fermat and the other mathematicians there.
Okay. Vanessa?
That was such a nice talk, Fran, and beautiful work. Some of our colleagues here are interested in axions and superradiance and so on. And it seems like it can do macroscopic things to black holes, like modify the spin and so on. You're not discussing, I mean, explain just how that would fit into your what you're discussing. Is it you're focusing on things that can happen like dynamically fast in a merger?
Yeah, or
and they're irrelevant for.
So actually, these actually might be relevant in a merger. So this I would sort of put on in this 3 classes. I'd say that those things would go on as sort of modified right-hand side. So we're saying it's still Einstein gravity, but there's now some new kind of matter that could influence the mergers. And you're right. So with these ultralight axions, I think there's a much sort of a more sensible motivation for why these might actually exist in nature. And so essentially the idea is if there's sort of order of magnitude, if you have a particle, a massive particle that has a constant wavelength that's on the order of the size of the black hole, so kilometers sizes, then if for a rapidly spinning black hole, there's essentially a superradiance that can spin down the black hole and sort of pump up can sort of create this cloud of this axionic field around the black hole. Now, typically the time scales over which that happen is much longer than the merger time scale. So it might, if those kinds of matter fields exist there, it might not be something that we can see in mergers directly, but it might, for example, be if you won't, if these things exist in certain mass ranges, you shouldn't see black holes that are rapidly spinning with comparable Compton wavelengths. So one thing would be looking at the spectrum of spins that have been observed. That actually is an interesting thing, is that the black holes that have so far been involved in LIGO's mergers, the progenitors don't seem to have very high spin. Another way which they might be visible in gravitational waves is when a black hole forms, and perhaps following a merger, it is spinning relatively rapidly over some time scale, which might be minutes, days, years. It depends very much on the properties of this axion. It will spin down, and then it will emit gravitational waves. And so there might be sort of some monochromatic sources that could be searched for. I think there are some people in LIGO and outside LIGO that are starting to look for those. And then there's another possibility that's perhaps a little bit more less plausible, is that if somehow, as the black hole spins down, there's potentially a lot of energy in the spin of the black hole, up to about 30% if it's extremal. If all of that energy can go into a cloud that's at least metastable, if it can survive for astrophysically interesting timescales, and if that black hole is then involved in a merger with another black hole with or without its own axionic hair, that could have a very significant effect on the signal in this merger regime. So people haven't yet sort of investigated those scenarios, but I think that would require that somehow these axion clouds that form would have to be stable on, perhaps millions or billions of year timescales, which, at least as far as I don't understand all the details of the physics of these alternative models, but it seems like that might be difficult to do. But sorry, long question, but yeah, there's a lot of interesting stuff that you can say with axion-like particles and ultralight matter.
Okay, Matt.
Right. So I think the point kind of Gregory and Massimo's questions was that if you're going to modify GR in a way that's consistent with its symmetries, then that's going to be in terms of invariant curvatures, and the invariant curvatures for black holes have a length scale that's kilometers. And so, whatever modification you make, it's likely to change things pretty drastically, either above or below that length scale, and then you'll be in trouble. So it's really hard. I think that's why, you're having so much difficulty in finding an interesting and viable modification within that class of theories. But, have you considered things that are sort of less tasteful? I mean, if you do something like break Lorentz invariants, like in your computer, you've got a lattice, and that's one way of understanding maybe why you had to work so hard to be able to simulate binary black hole mergers and get anything that's consistent with GR. You had to deal with the fact that the constraints are being violated by numerical errors, et cetera, et cetera. So, if you do something like that, you get a theory that has very strong modifications at the horizon. Now, it might not be viable or interesting for other reasons, but are you thinking along those lines, or are you really sort of committed to preserving Lorentz invariants and so on?
No, not. Well, I think for me the most sort of important thing is to have something where there is a well-posed problem, and it's, even if you might have to go into contortions to justify it, at least it's plausible. So, for example, one class of things that you could do is just add right-hand sides to the Einstein equations and say, okay, that's going to affect the geometry in some way. I think it will be difficult. From the point of view of the Einstein equations, it would be more difficult to modify the speed of light in a way that is anything more than just a change of scale. But even if you do that, I think that the problem is there's a question of, let's say, garbage in, garbage out. Like, how can you justify what you do? Because it's something you can almost do if you're allowed to, like some of these, like you can come up with any geometry you want, essentially, and then just shove all of the effort onto the right-hand side. And then the question would be, well, what are you actually going to get out of this? That's an interesting prediction. And so that's sort of the bar that I would have some modification must cross before it's possibly worth testing, is that from a classical sort of a mathematical partial differential equation language, that it's a well-posed theory, and it's not something ad hoc where I can get any answer I want by just adjusting certain things. I'm not sure if I answered your question, if that's exactly what you were going after, but
can I this is Kyle. Can I sort of follow up with that? Maybe so at the Large Hadron Collider, we had a kind of similar situation, in that there's like the standard model. It's very well constrained. We found the Higgs boson, which is kind of like roughly the equivalent of GR in terms of satisfying all these consistency requirements and things. And then you would like to have some kind of set of deviations about it that you could go around testing. And there, at least, we have a nice set of options in the context of what's called effective field theory, where you add additional interactions, and there's a kind of very kind of standard expansion that you can do around the standard model. But before that was done, because computationally it requires a lot of infrastructure, somewhat analogous to what you would need to establish the infrastructure for testing one of these extra, one of these other theories. And so before that happened, there was this program that was done, which was basically to modify, in a statistical sense, to like modify the predictions for the data in a very like empirical phenomenological way that does not map onto a ultraviolet, UV complete theory that has all the nice properties that you would want. It was basically just very, from the experimentalist point of view, it's just like, well, what if I saw more decays of this type than I expected? You're really just modifying the data, like really at the level of something that's very intuitive to understand in terms of what's happening. Like there's like more radiation here than I expected. And then we could parameterize that in a very straightforward way that's very kind of easy to interpret from a observational point of view, and measure those constants where they should be zero if it's a standard model. But the problem was that there was a lack of how to attach that to any kind of theory that anyone understood from the point of view of field theory. And it seems like there's very much a analogous problem here. And it seems, what I'm a little bit curious if there's, I think it's along the lines of Matt's question, is if there's some sort of deviation that's kind of more in the space of the data that can be tested that might not obviously have a connection to some sort of theory of gravity, modified theory of gravity. But if you saw deviations in that kind of particular basis that's motivated in some way, you would they're not just like generic residuals, like a car ran over some railroad tracks or something. They're like they look like physics, right? So what I'm curious is if there's some sort of language for describing residuals or deviations from standard gravity and GR that's in that language, where later you would work harder to try to figure out how to map it onto some kind of meaningful theory.
Yeah, good question. And yet there are, and in particular for the perturbative aspect. So the in spiral, and so there the starting point is sort of a post-Newtonian or effective one body, or there even if effective field theory approaches to looking at sort of binary dynamics. And then you've got sort of an expansion in terms of some parameters, for example, V over C, or the frequency of the binary. And then in certain cases, you can say, well, okay, this might not be sensible, but let's change the relationship between the binding energy and the radiation that's emitted. So let's modify the Kepler law. Let's say there's an extra degree of freedom, and then just apply it to those perturbative equations and see how it modifies a waveform. And then you can just, based on that, you can sort of generalize the expansion, so that each sort of additional power of V over C that comes in this post-Newtonian expansion, you just say, well, let's just search for generic modifications. And actually, this is one thing that I sort of skipped over, but is what LIGO is kind of doing that. And this is this one figure. So they've placed upper limits on deviations from these are the so-called post-Newtonian expansions. So there is some of that is going on. On another side, and perhaps this will also address sort of Matt's question, where I was kind of worried about like garbage in, garbage out. But for example, and I apologize if I offend anyone, but one class of this that I often pick on are these gravistars, or these sort of these horizonless ultra compact objects. And the idea is that that will modify, so this is the in spiral. So in that case, the argument is it will modify the ring down. If you don't have a horizon, you've got some finite surface, then you will get echoes of this ring down signal. I think, as an idea, it's fine. I have no problem with that as an idea. On the other hand, there's no theory that gives you these kinds of objects. The way that they've been constructed is essentially, you assume that that's what the geometry is. You plug it into the Einstein equations, and that tells you what exotic matter you need at the surface to, say, transition from a Schwarzschild exterior to a de Sitter interior. I think that was the original gravastar. But then the thing is, because then, okay, if that is your object, it would be very surprising if that didn't influence the dynamics of a merger when two of these things collided before it, assuming, again, you have to assume that it then very quickly settles down to a new stationary gravastar that then can produce this echo. But it seems, to me, it almost seems like it would be crazy not to see the signature of that in the in spiral, but only in the whole merger waveform, and only see echoes at late times. And so then you can also imagine, well, let's concoct a gravastar merger by taking two of these objects and just putting the trajectories in by hand. We'll be able to get a geometry. We'll be able to look at, sort of a binary gravastar. But I think the answer that you'd get would be exactly what you put in. So that class of modified things, I'm less excited about. But this former class, which I think is similar to what you suggested, what Alish is doing, modifying sort of a well-defined perturbative approach to the in spiral. I think that's quite sensible. You don't have to have a particular theory, and then it could be, well, at some point, with more and more data, when they get these exclusion limits lower and lower, at some point, perhaps something pops out. And here, for example, that would give you some information. So depending on the p-n order that it comes in, it might look like an extra degree of freedom, say spin 1 degree of freedom, or I think a scalar degree of freedom is at the negative Pn. So that's something like the binary pulsars are sensitive to. But at I think at 2 Pn, you'd get effects that look like tidal effects, like what neutron stars would give. And in certain specific theories of gravity, or even propagation effects, for instance, violations of Lorentz invariance, they would show up at various of these Pn orders. And then, yeah, so you'll be able to notice them. You'll be able to say more about what's going on in this pure residual test without actually having to have a particular theory that tells you what, or gives you that prediction.
Great, thank you.
Okay, do we have any last questions for Frans? Okay, if not, let's thank Frans again.
Thank you.
Thank you, everyone. And sorry for going a bit over. Everyone have a good day and stay safe. And hopefully I'll see you in person, not too far into the future.
That would be great. Yeah.
Great, thank you.
Thanks again.
Can I want to ask a little naive question, and so I wanted to let everybody leave. Following up the question I asked, when I was, you articulated it well at the end. It seems like if a substantial amount of the mass of the spinning black hole gets instead somehow in this extended halo of axions, and then those objects merge, it seems like the gravitational waves could be pretty different, because there's a lot of mass out there. And I just was curious if people try to simulate that. I mean, I understand that as I understand it, I'm not an expert by any means, they have to sort of fine tune the axion parameters to have a big impact on a given mass. But there are ranges of axion parameters. I wish Masha were here, but I guess she's not. Anyway,
He signed off
we have a couple of
ago. But I think I can answer that question, Glennis.
You know the answer. Okay.
Yeah, so these ultralight axions, if their Compton wavelength matches roughly the Schwarzschild radius, they can spin down the black hole quite efficiently, this exponential runaway superradiant effect. But this spin down happens only under certain conditions. So for an isolated black hole, or perhaps in a binary when the binary is quite well separated. So basically the spin down of the black hole happens at large separation. And then what you would see in the final merger event is just lower spinning black holes, you know, and
So why won't they carry their axion cloud? The question I had is,
so it does,
why
but
don't
the
they
tidal, yeah, the tidal field of the companion will disrupt the cloud, basically to the point where when you see it in LIGO, that cloud has vanished, like it's been tidally disrupted and is no longer part of the system. So
or maybe it's just a really big cloud or something, and it's not concentrated enough to matter.
Right. I mean, it would be something like an accretion.
Of the mass, it's a lot of energy. It just seems like if there's all that energy around, it might have an impact. It would be interesting for somebody to simulate it.
So in Masha's work, I think the total mass of the cloud can be up to, let's say, 1% or a couple percent of the total mass of the black hole. So you can extract a lot of the angular momentum of the black hole, but not necessarily the rest mass energy.
Well, that was what a number that Frans mentioned that sort of confused me, because I was aware of it's taking all the spin, but I thought he was just saying that the spin can actually be accounting for a third of the energy. Did I mishear that, Frans?
Oh, yeah, you're right. So
maybe that's a different.
Yeah, if you could spin down an extremal black hole all the way to the Schwarzschild black hole, theoretically you can extract 30% of the energy. But I guess the issues with these axion clouds is how much of that is going to stay. Okay, so the initial spin down is fast, but it's also it slows down very rapidly. So to get all the way down to Schwarzschild probably is going to take longer than the age of the universe for most of these things. So it's really just
I see.
So they
get a few percent, like the number Ken was quoting. But so what I don't understand is how could you say it's taken? So I see. So the point is it only actually no, but how can it spin it down macroscopically? Let's say from specific angular momentum 1 down to a third, right? Because the claim is that the spins, if you went out and observed spins of black holes, you should get a much smaller, you shouldn't get big spins, as I thought the claim. And so that means I would have thought naively, or is it that very last bit that's carrying all the energy? That's what's confusing me about this.
Sorry, no, it is, right, so yeah, so if you spun it down to 30%, yeah, that would be, you know, a big, it'd be much more than a percent, 10, 15, 20%. But I think the claim is that most of that doesn't stay around in the cloud.
Yeah, that part I guess can explain that it gets.
Yeah,
it just-
and one small number is also that, you know, the non-relativistic solutions can carry a lot because they have a larger radius in general. They can carry a lot of angular momentum per unit rest mass energy.
Yes, fair enough.
So that's
Fair
why
enough.
you can spin down a black hole by order 1, yet have it lose a small amount of rest mass energy.
On
Not
the
make
other
much impact.
on the other hand, like 1% is actually from the total gravitational wave emission perspective is quite large, right? So these, you know, the whole in-spiral merger ring down, it's losing 5%. So 1% is actually quite a bit. And so if, you know, if, I don't know, perhaps if you can like tune the potential of the axion, then you can have the cloud be a little bit more tightly bound. So in the regime where it is being tightly stripped, that will have a very significant effect on the dynamics. And so if that regime could be observed, you know, perhaps LIGO, you might have to go to frequencies that are too low for LIGO. But you know, I think that would have, if you could see the phase where they were losing their clouds through tidal effects, that would have a very strong influence on the evolution of the orbit, and that would be visible. And if some of it was still left over at the time they merged, I think that would also be quite a significant impact on the dynamics, which should be visible.
I just brought it up in the spirit of what you're looking for in a way are concrete concrete examples that maybe delving into them in depth gives you a new idea for what's you know, a phenomenon that might vary. I have some noise in the background, so I better say goodbye. Thank you again.
Welcome, thank
Bye
you.
now.
Okay, great. Thanks again, Frans.
Thank you.
Welcome. Bye, everyone.
Bye.